We want to begin talking about two different things that are very much related. The first of them is the idea of center of mass, and the second one is linear momentum. So let's start off by looking at a couple of objects on a line. So here's a line here, and there's a large object here, and maybe a smaller object there. And you can think of like a teeter-totter when you were growing up. You have a large child on one side and a smaller child on the other. How would that balance? You know, the teeter-totter is set up in the middle like that. That's where the fulcrum is. And the larger child will always be weighing down the smaller child. And so what had to happen in order for the fulcrum to allow balance? Well, the larger child would have to move in. So when there is a balanced scenario, then the fulcrum is at the center of mass. So in this case, the fulcrum might be someplace like that. Well, that is where the center of mass is. And oftentimes we'll symbolize the center of mass as a circle split into quarters, and we'll shade in two opposite corners. So the center of mass on this line is defined using this relationship right here. And what this is saying is that, so we assume I have n particles, n discrete particles. Discrete means individual particles, and we'll look at continuous objects here in a little while. So in this case, n is equal to 2. And so when I want to find the center of mass, I'm going to label this m1, and its position is x1. And then this is m2, and its position is x2. Then the position of the center of mass is m1 times x1 plus m2 times x2. And this is the x-axis, of course. And then I'll divide that whole thing by m1 plus m2. So this denominator is the sum of all the individual masses. And the numerator is the sum of the product of the mass times its position. Some of those will be positive and some of them will be negative positions. Of course, mass is always positive. In 2 or 3 dimensions, we do the same thing, except instead of multiplying by the x position, we multiply by the vector position. So it'll have an x and a y and possibly a z position there. So we'll run through an example here. I've got 3 particles, so it's going to be a summation I equals 1 to 3 of m sub I r sub I, that's a vector quantity, divided by the summation I equals 1 to 3 of m sub I, where I then is 1, 2, and 3, m1, m2, m3, r1, r2, r3. So the denominator is very straightforward. That's going to be 5 kilograms plus 10 kilograms plus 20 kilograms. And the numerator is going to be 5 kilograms, and I'm going to use a coordinate system like you would on an xy plane, only I'll have x, y, z. So it's going to be 5 meters, 3 meters, negative 1 meter, plus 10 kilograms times 4 meters, 2 meters, 5 meters, plus 20 kilograms times negative 3 meters, negative 2 meters, 2 meters. So the denominator here is 35 kilograms. And the numerator is going to be 5 kilograms times 5 meters, so that's 25 kilogram meters, plus 10 kilograms times 4 meters, so that's 40 kilogram meters, plus 20 kilograms minus 3 meters, so that's minus 60 kilogram meters. And that's all the I components put together. And then the J, I'm going to have 15 plus 20 minus 40, so 15 plus 20 is 35 minus 40, so that's negative 5 kilogram meters in the J hat direction. Then I have minus 5 kilogram meters plus 50, so that's plus 45 kilogram meters, plus 40, so that's plus 85 kilogram meters in the K hat direction. And so in the end, I have 5 kilogram meters I hat minus 5 kilogram meters J hat plus 85 kilogram meters K hat all over 35 kilograms. And so you see the kilograms going away, which is good because this is a position. And so I'm going to get 1/3 of a meter I hat minus 1/3 of a meter J hat plus 17/3 of a meter K hat. And that's the position of the center of mass of these 3 particles. Now for continuous solids, I'm going to take that summation. Let me just go back to the sum of the m sub I, r sub i's. And imagine, if you will, I've got this object I like to think of potatoes because they're unusually shaped. None of them are the same. And if we take a little bit of this potato, a cube of it, then put it onto a coordinate axis, so that little bit of a potato there has a position r sub I, and it's got some mass dm. It's a very small portion of the entire potato, so the mass dm is just a part of the entire mass. And then I'm going to add up all these little cubes of potato. Each one of them has a different position. That might be R1, R2, and R3, etc. And I'm going to add them all up, but there's an infinite number of them. So the idea is that each of them has a mass dm, and I'm going to sum over all those dm's. Well, that's what an integral is. As dm goes down to infinity, the summation becomes an integral. And so I integrate all of their positions with respect to mass. Now that's kind of an interesting concept. You're used to integrating with respect to a coordinate, like an x or a y or z. But now, in physics, we start integrating with respect to something different. In this case, mass, because I'm summing over all the mass of the potato. Same thing down here. Now this is just the total mass of the potato. Now in some cases, the object might have a uniform density, same mass per unit volume or mass per unit area or mass per unit length. Those are all densities. And so it's got the same mass per unit density, and then the integration is actually fairly easy to do. But sometimes it's not. Sometimes the integral is kind of tough to figure out. And that's kind of what we're going to be trying to do. We're going to try and figure out what that integral is. So here's another example. Now in this case I've got two thin uniform rods. Now the beauty of a uniform rod or a uniform shape is that the center of gravity is always at the geometric center of the object. In this case that's going to be right here and right here. There's the center of one and there's the center of the other. They each have the same length and they each have the same mass of 0.02 kilograms. So the question asks for the x and y coordinates of the center of mass of the two rods. Well, that's really not going to be too bad. So the center of mass of the top rod is at 0.1 meters in the x and 0 meters in the y. And it's got a mass of 0.02 kilograms. So 0.02 kilograms times 0.1 times 0.1 meters in the I and 0 meters in the j. Then I add to that 0.02 kilograms again, because they both have the same mass. The center of mass of this one is at 0.2 meters in the I, minus 0.12 meters in the j. And of course the total mass is 0.02 kilograms plus 0.02 kilograms. And so I get 0.002 kilogram meters in the I plus 0 in the j, because that's 0 right there, plus 0.004 kilogram meters in the I minus 0.0024 kilogram meters in the j. And then we divide that by 0.04 kilograms. And again, all the kilograms will divide out. This is all the position of the center of mass. So I'm going to have 0.006 meters in the I minus 0.0024 meters in the j, all over 0.04. And that's going to equal 0.15 in the I minus 0.06 j. And that's all meters. And that makes sense because that should be pretty much right in between there and right in between there. Well, halfway in between 0.1 and 0.2 is 0.15, and halfway between 0 and 0.112 is 0.06. So that seems to work out really well. Now if one had more mass than the other, it wouldn't be halfway in between, but because they're the same mass, it's going to be uniformly in the middle.